So welcome to the next section of our chemistry unit, which is organic chemistry. So the first thing that you need to know is the difference between organic and inorganic substances. So organic substances are usually derived from living organisms like trees, plants, things like that, or oil and gas, which oil and gas came from trees and plants and algae and stuff like that. That's where that came from millions of years ago. So there are about 50 to 60,000 known inorganic substances. So inorganic is everything that we were doing before with the sodium and hydroxide and acids and bases, but there's over 4 million known organic ones. So these are all organic substances. So foods, fuels, greases, fabrics, wood, antibiotics, perfumes, flavors, explosives, paints, plastics, dyes, soaps, fertilizers, right? So a lot of different things that are super important to us are organic, and all of these things would be either from oil and gas or from plants or living organisms. So organic compounds, the way you can spot them is if they have carbon and hydrogen mostly. They can have other things in there like oxygen, but mostly you have this long carbon chain with hydrogens all around it. So you need to know how to draw them. So Lewis dot diagrams show a dot for each electron in the valence shell, and you did this in Science 10. And structural diagrams show a bond as a line, and you might have seen these in other sciences, but probably haven't done structural diagrams yet unless you've taken other chemistry courses. So in structural diagrams, you have double bonds, which show a double line, and triple bonds are a triple line. Okay, so we can do an example. So we have CH4. So for CH4, I should have kept my camera open. Let me open up my camera here. Let's do it on this. Just give it a sec to open up. Switch that so it's upright. Like that, and make it a little bit brighter. Perfect. So to do CH4, to draw it out, I usually like to start off with a Lewis diagram. And in my Lewis diagram, I draw carbon. Let me grab a data booklet here. So if you have your data booklet available, open up to your periodic table. And what I want you to notice is these numbers up here. So these numbers are your group number, and those will tell you how many electrons they have in their outer shell. That's what the valence shell means. So we can see carbon here is in group 14. So we take the last number of 14, which is 4, and if we take the last number of 14, which is 4, it tells us that there are 4 electrons in carbon on the valence shell. So there's 4 spots with 2 seats, and no one likes to sit beside each other unless they have to. So if we have 4 electrons, one will go here, one will go here, one will go here, and one will go here, and no one has to double up, right? So what that would look like is like that. And then we have hydrogen, which is in group number 1. So hydrogen has 1 electron in its valence shell. Okay. So what we're looking to do is we're looking to make sure that all these guys are paired up. So we're going to switch to a structural diagram after this. So we have 4 unpaired electrons. So that means that carbon needs 4 sticks attached to it. And hydrogen has 1, so it needs 1 stick attached to it. Okay. And we want to start with our atom with the most unpaired electrons, which is carbon. So if I draw carbon, carbon needs 4 sticks attached to it. And hydrogen only needs 1 stick attached to it. If we look at CH4, well, we have 1 carbon that we're dealing with and 4 hydrogens. So voila. Look at that. We have what our CH4 molecule looks like. Each hydrogen has 1 stick and each carbon has 4 sticks. So let's try another one of those. So another example is NH3. In our data booklet. So nitrogen is right here. Oops, I'm not on my camera. nitrogen is right here, and nitrogen is in group 15. So if I drew nitrogen, it would have 1, 2, 3, 4. Now all the spots are filled up, so one of them has to pair up. So there, nitrogen is paired up there. And then we also have hydrogen, which has 1 like before. So this needs 3 sticks attached to it, and this needs 1 stick attached to it. And it says our molecule is NH3, so nitrogen needs 3 sticks attached to it, hydrogen needs 1. So that's what it's going to look like, NH3. Right? And that's why it's NH3, not NH4, because, well, it'll need 3 sticks attached to it. Okay. So I'm going to do one more example with double bonds. Oops. So this one here, we have carbon and nitrogen, so C2N2. And we're not going to be able to do this with just single bonds. So I'm going to write that up, C2 and N2. And I'll switch cameras to this here. So we have carbon, which we know is in group 14, and it's like that, and we're dealing with 2 of them. And then nitrogen has 5. We have 2 of them, so this needs 3 sticks, and this needs 4 sticks. And usually if we have carbons in there, they usually pair up together. So we make these carbon chains. So I'm going to put my 2 carbons together. Now, remember that we need 4 sticks attached to each carbon. So if I just put a nitrogen over here and a nitrogen over here, well, no one would really be happy because each of nitrogen only has 1 stick, carbon only has 2 sticks. But if I put this, well, that's a little bit better. Now this carbon has 1, 2, 3 sticks. This nitrogen is 2. What if I add just 1 more? Now nitrogen is 3 sticks attached to it, carbon has 4 sticks attached to it, and we're all good. And if we do the same thing on the other side, then that's what it looks like. So we have a triple bond here and a single bond here. So that's how we would draw those triple and single bonds. So there's 3 different names that are going to come up: alkanes, alkenes, and alkynes. So if you only have single bonds, then you're known as an alkane. Okay. So this is from our data booklet, and this is on page 9 of our data booklet. It's in here. So this shows an example of an alkane. You can see it only has single bonds like that. An example is ethane, which we'll learn how to do. Double bonded carbons, they are alkenes. So if we have 2 bonds, a double bond, not 2 bonds. If we have a double bond here, which shows right there, then you are an alkene. And if you have a triple bond, you're an alkyne. And this picture kind of smudged a little bit. It'll be better in your data booklet, but you can see that there's 3 lines there. And that's what makes an alkyne. So we're going to start off with the easiest ones, which are alkanes. So alkanes are given this formula, which is CnH2n plus 2. And I'll explain what that formula means. So we're going to start off with, let's start off with 2 carbons. So if we have 2 carbons, it's given the name eth, right? So 2 carbons, remember that the carbons always go beside each other like that. And each carbon needs 4 sticks attached to it. And what we do with alkanes is we just fill those other sticks with hydrogen. So there'll be a hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here, and a hydrogen here, right? So each carbon has 4 sticks attached to it. Each hydrogen has 1 stick, so it's all good. And if we wrote out this formula, it would be C2, and then we have 1, 2, 3, 4, 5, 6, H6. Okay. So what this formula means is that if N is 2, right, C2, well, H is going to be 2 times N, so 2 times 2 plus 2. Right, so 2 times 2 is 4 plus 2 is 6. So you can use this formula to figure out what the formula would be, or you could just draw it out like that. Okay, I'll do another example. Let's do one more. I'll do propane. So propane means prop means we have three, ane means it's single bonds, right? So meth means one, ane means single bonds, eth means two, single bonds, prop means three, ane means single bonds, bute means four, ane means single bonds, like that. So if I want to do propane, prop means I have three carbons, and I'll just make sure that each carbon has 4 sticks attached to it, and I can fill those with hydrogen. Like that. And then my formula for propane would be C3, and then H1, 2, 3, 4, 5, 6, 7, 8, H8. And we could go on, but yeah. So you need to know what these root words mean, and they are all on your data booklet on page 9 as well. So it gives you that information on page 9, which I think, yes, right here in my data booklet. So it'll tell you this: meth means 1, eth means 2, prop means 3, bute means 4, pent means 5, hex is 6, and so on. So all that is in your data booklet, so you don't have to memorize it. Okay, there's different ways to depict organic compounds. So there's a molecular formula which gives you the least amount of information, and that's just what's there and how many are there. An expanded molecular formula is a little bit better because you have the things here, and what that indicates to us is that's a branch. And I'll explain what a branch means when we get to the next type. So structural formula shows it really nicely, and you can see that this is our branch here. So we have this carbon chain, this chain here, and then we have this branch that sticks off, and that's what this represents. Okay, we'll do some examples with these. And then there's a condensed structural formula. It's annoying drawing all the H's every time. So what that does is it condenses all those H's into CH3, so you don't have to draw an individual H every single time. And then the last one is a line formula, which people find a little bit confusing at first, but it shouldn't be because it draws it nicely. So this, each time it switches direction, indicates a carbon, right? So we have a carbon here, carbon here, carbon here, carbon here, and then we have a carbon at the end. What it doesn't show is it doesn't show the hydrogens, right? So it's the same thing. We have 1, 2, 3, 4. All these are the same, different drawings for the same thing. So we have 1, 2, 3, 4, and then the branch. So we have 1, 2, 3, 4, and then the branch that comes off. Okay, so if you take an alkane and you remove the hydrogen from the molecule, you'll create a branch, which is a side group, right? So if you want to stick a branch on, you got to remove that hydrogen there, right? This is an alkane, and now this can work as a branch because you can stick this on somewhere, right? Same thing with this. You take off a hydrogen, it can work as a branch. So when it becomes a branch, it still has that normal beginning name, right? So this has 1 carbon, and 1 carbon means meth. But since it's a branch, we add a ol onto it, right? This is 2 carbons. 2 carbons is F, and then we add an ol onto it. So these are our rules for naming alkanes with branches. So first step is you get the parent name from the longest carbon chain from end to end, and then you can box that parent. You identify the name of any alkyl groups. You try counting from either side of the chain and use the lowest number combination for alkyl groups, and then name your alkyl groups alphabetically. And if there's 2 possibilities where it's the same numbering, you give the smaller number to the branch that's lower alphabetically. So this won't make sense now, and that's okay. But we will go through some examples. Okay. These are also for formatting your alkanes. So we use hyphens to separate numbers and words, commas to separate numbers, di and tri prefixes when there's more than one of the same alkyl group present, and no spaces are used in words or numbers, and nothing is capitalized. Okay, so these are just some rules. So I will go through this one. I will do some examples. We're going to name this compound, or we're going to draw it using line structure, and we're going to name it. So let's start off with drawing it with line structure. So we have 4 carbons here. This is our parent here. And then we have a branch that sticks off. So if I wanted to draw this with a line structure, I would go 1, 2, 3, 4, right? I'm counting the dots that I draw, not the lines. So this is 1 carbon, 2 carbon, 3 carbon, 4 carbon, and then we have a branch coming off here, our second carbon. So it would look like that. Okay, that's what our line structure will look like. I'll do another one on the next example. So if we want to name this, first thing we do is we're going to box our parent. So we have 1, 2, 3, 4. 1, 2, 3, 4. Yeah, we can't get any longer than 4 here. So these 4 are our parent. And if we look up what 4 is, 4 means butane. So our parent is butane. Okay. Coming off of here, we have a branch, right? Our branch has 1 carbon. So this is a methyl branch. Now, this methyl branch, we need to indicate which carbon it appears on. So I could count, this is carbon 1, this is carbon 2, this is carbon 3, and this is carbon 4. Or I can count from the other way. I can say this is carbon 1, this is 2, this is 3, and this is 4. So this branch appears on this carbon right here. What we can do is 2, or we can do it as 3. Well, 2 is a lower number, and that's what we want to use. So this is 2-methyl. So to name this, we would just add that 2-methyl. And I want to put a dash between numbers and words and no spaces in between. And the name of this is 2-methylbutane. Okay, I know this seems a little bit overwhelming at first, but I promise you it gets easier. Okay, if we want to name this one here, first thing we're going to have to do is find our parent. So sometimes you have to be careful. You can count from any end that it starts on. You can count here, 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 or here, and see how long your parent chain is. So if I just go straight across, 1, 2, 3, 4, 5, 6, 7 carbons. I could count here. I could go 1, 2, 3, 4 carbons. I could start here, 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5. So it looks like no matter where I start from, 7 is going to be my longest carbon chain. So that gives me my parent name, which is heptane. Okay, hept means 7, ane means it's only single bonds. So now that I have that, I have 2 branches. This branch has 2 carbons on it, which is an ethyl, and this carbon is a methyl. So now we just need to indicate which carbons those go on. So we can count this way. We can go 1, 2, 3, 4, 5, 6, 7, where they would be on 3 and they would be on 5. Or I can count this way, 1, 2, 3, 4, 5, 6, 7. And if I count that way, they can be on 3 or 5. So either way, they're going to be on 3 and 5. So it doesn't matter which way you count from. But this was that little rule that I talked about in here. If both are 3 and 5, what you want to do is you want to give the lower number to the first number that comes in the alphabet. So E comes before N. So I want to make this my 3, and I want to make this my 5. Okay. When naming these, I want to name them in alphabetical order. So E comes before M. So I would call this 3 ethyl, 5 methyl, heptane. Okay. So I'm going to do one more, and then I'm going to do some board questions. So what you should do after this is just pause the video and then try to do it yourself. And then I'll go through an explanation and we'll see how it works. So this one's kind of tricky because it's like, ooh, is 1, 2, 3, 4 our longest carbon chain, or is it 1, 2, 3, 4, 5, 6? Ooh, right? So if I do this, that's actually my longest carbon chain. 1, 2, 3, 4, 5, 6. It doesn't have to be straight. It just has to be kind of like without lifting your pen up. So 1, 2, 3, 4, 5, 6. 6 is hex. Oops. And all single bonds, which is ane. And then we have 2 branches coming off. Okay, so we can, so this is a methyl branch because it has 1 carbon. This is a methyl branch because it has one carbon. And we can number 1, 2, 3, 4, 5, 6, or we can do it from the bottom. We can number 1, 2, 3, 4, 5, and 6. So if we number this way, we get 3 and 4. If we number this way, it's 3 and 4. And it actually doesn't matter which way we count because both of them are methyl, so none of them are lower alphabetically. So we would just indicate that we have methyls on 3 and 4. And because we have 2 of them, we call it dimethyl hexane. So we have 3 and 4. There's 2 of them, so 3,4 dimethyl hexane. That is my name. Okay, so we're going to start off with some easy board questions. So pause the video here, try it yourself, and see if you can name it. Okay, so our longest parent chain is this. We have 1, 2, 3, 4, 5. So our parent is pentane. And we can number 1, 2, 3, 4, 5. Or we can number 1, 2, 3, 4, 5. Right? So it can either be 2 or 4. So we're going to go with the 2 because it's lower. And then this here is a methyl group because it just has one carbon. So it's a 2-methyl. So we'd add that to our name. So 2-methyl pentane is the name of that. Okay, let's try another one. Again, pause the video. Okay, so we got to be careful with this one. We can go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. So it looks like 4 is going to be our longest chain, and 4 is butane, like that. So we have 2 methyls sticking off here. So this is a methyl, and this is a methyl, like that. And yeah, so we can count 1, 2, 3, 4, or 1, 2, 3, 4. So either way, it's going to be 2 and 3 or 2 and 3. So it doesn't matter. So we have 2 methyl groups, which are on 2 and 3. Use a comma to separate numbers and a hyphen to separate words. And because there's 2 of them, we have to use that di prefix. So it's dimethyl butane. Okay, let's try another one. This one's super tough, and I think, oh, we have one more after this. Okay, so this will be our second last example, and then we're gonna continue the rest of the stuff on Tuesday. So pause the video here, try it yourself. You got to be really careful with this one because you got to find your longest chain. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, this is our longest parent chain here, which means we have a methyl coming off of here, and we have an ethyl coming off from here. Okay, so our parent is 1, 2, 3, 4, 5, 6, 7, 8. So octane is our parent. And then we can count 1, 2, 3, 4, 5. So that would give us 3 and 5. Or we can count 1, 2, 3, 4, 5, 6, which would give us 4 and 6. So that's a bigger number, so we don't want to use it. So we want to use 3 and 5. So 1, 2, 3, this is 3-methyl. 4, 5, this is 5-ethyl. And we want to name them alphabetically. So the 5-ethyl would come first. And then we would have the 3-methyl next. Okay. So our last board question for the day. Sorry, I changed. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I must have changed the question, but didn't change the answer there. The way that we drew it is correct. I think I made it a little bit easier. Okay, so this last one, which kind of looks like a dead stick man here. Murder scene. So the last one here is a line diagram. So remember, we want to focus on, actually, let's change my color to red. I wanted red, not brown. There we go, that's better. We want to focus on all those intersections there, because those are all carbons. Remember, pause this, try it yourself, because there's no assignment on this one. So these board questions will be your example. So these are all our carbons. We need to find our longest carbon chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it looks like the longest carbon chain is going to be 6. And it actually doesn't make a difference if you included these two or these two, because it would end up being the same. So we have 1, 2, 3, 4, 5, 6. So our parent here is hexane. So we have this guy with just one carbon coming off. So this is a methyl. And this one has 2 carbons coming off, which is an ethyl. Right? So we can count this as 1, 2, 3, 4. So that would give a 3 and 4. Or we can count it as 1, 2, 3, 4. We get 3 and 4 no matter what. So we're going to give our lower number to our lower alphabetical. So 3 goes to the ethyl, 4 goes to the methyl, and then we name it alphabetically. So 3 ethyl, 4 methyl, hexane. Okay. That's all we're going to do for today. We'll do some more stuff tomorrow. So hopefully those board questions went well. And yeah, let me know if you have any questions. 2 of organic chemistry. Okay, so yesterday we did just alkanes, and now we're going to add on some alkenes and alkynes, which have very similar rules. So a saturated, you may see this term come up, a saturated hydrocarbon contains just single bonds. So if you think of the word saturated means like it can hold as much as it can possibly hold. So when we're talking about what it can hold, is it can hold as many hydrogens as possible. So this is something that is saturated. It's holding as many hydrogens as possible. But as soon as we put in a double bond, right, it becomes unsaturated because that double bond makes it. Remember that each carbon can only have 4 sticks attached to it. Well, now the carbons aren't holding as much possible, right? Because each carbon could technically hold 3 here, but now each carbon's only holding 2. So that's why it's called unsaturated. So if you have a double or a triple bond, if you're an alkene or an alkyne, then you are unsaturated. Right? And unsaturated are really important. They make plastics, and yeah, they're really important in the oil and gas industry. So you need to know some examples of everyday things that are used, or everyday organic compounds that are used. So I don't know if you've seen these Debbie Meyer green bags. There's lots of other versions of them. But how Debbie Meyer green bags work is fruits, vegetables, and flowers release ethylene. So there's different names for things. So the ethylene is a common name. We call this ethene. So fruits and vegetables release this ethene gas, and after they are harvested. So ethylene or ethene gas accelerates the ripening process, and what Debbie Meyer green bags do is they absorb and remove this gas, which can extend the life of your flowers or fruits or vegetables. So in this picture they show bananas here. These are from the same bunch, so these are in the bags, these are not in the bags. You can see that these peppers are all rotten, these ones are not, and these tomatoes are all rotten, and the ones in the bag are fine. So ethene gas, what it does is it helps accelerate the ripening process. And sometimes if bananas come to a warehouse and they're all green, they'll spray them with ethene gas, which can speed up that ripening process and just make them more yellow and delicious, because green bananas are gross. So alkenes have the general formula of this. Alkenes are identified by the presence of at least one double bond, and you can't have a one carbon alkene because you need at least one carbon-carbon double bond. So the simplest alkene is going to be this. And if you remember from yesterday, if we have two carbons, it has the root name F, and how everything ended in ane last time. Well, if it's an alkene, it ends in ene. So this is ethene, this is that fruit and vegetable ripening gas, and that's the simplest hydrocarbon we can have. So naming rules are very similar. So establish the longest continuous chain. That includes a double bond. Carbon 1 is going to be closest to the double bond. So this is a little bit different than alkanes. The pair name ends in ene and has a number added directly before it to indicate which carbon the double bond follows. And branches are named just like alkanes. And when the alkyl group can be listed on 2 or 3, always use a smaller number. I'll show you an example. So we need to indicate where that double bond is. So instead of just saying butene, we say but2ene, and this is where that double bond occurs. So but means 4, 2 is where the double bond occurs, and ene means that we have a double bond. So we can express it all the same ways as we showed before, right? Remember that these brackets are branches, so we just got this double bond in here now. And this is how we do it in the line structure, just draw a double bond. Okay, so let's do an example. So we're going to name this. So we find our longest carbon chain. So we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, it looks like 7 is going to be our longest one. Okay. In terms of counting, we care about the double bond, not the branches. So we can count 1, 2, 3, 4, where that is between 3 and 4, or we can count 1, 2, 3, 4, 5. So now the double bond's between 4 and 5. So we want to count this way, the first way I did, because that gives us the smallest number. We don't actually count the carbons, we count the bonds. So this is bond 1, bond 2, and bond 3. So we have 7 carbons, which is hapt. And you can look that up in your data booklet. This is bond 1, bond 2, bond 3. So we use dashes to separate numbers and words. And because it's a double bond, we end it in ene. Okay, so that's new. Branches are the same. Okay, so we have 2 branches here that are methyl. And then we have an ethyl over here. Okay, this is methyl as well. So we already established that we start counting from over here. So this is carbon 1 and this is carbon 2. So now we count the carbons, not the bonds. So carbon 1, carbon 2. So this is 2-methyl, this is 2-methyl. And then on the third carbon, we have our ethyl. So we name them alphabetically. So the ethyl comes first. So we go 3-ethyl. And then we have 2,2. So those are where they occur. And since there's 2 of them, we have to call it dimethyl. So the name of this is 3-ethyl 2,2-dimethyl hept3-ene. Okay, let's do another example, and let's draw a line diagram for this as well. So this is this condensed structural formula, which is annoying. I like to draw it out as a structural formula. I'm just going to use these as H's to save a little bit of time. So this is CH3, and then we have CH, and then you can see this is a branch that comes off. So I have a CH3 branch that comes off like that, and then we have CH, so the line will just represent H, and then we have this ethyl branch coming off, CH2, CH3, and then we have CH2, and then we have CH2. Okay. So now what we're looking for is, we know this is an alkene example, so we're looking for where we don't have a, oops, I should have drawn this on. It's a CH, not CH2. Or, sorry, we have our ethyl, and then, we have CH2, and then we have CH, sorry, I drew this wrong, and then CH2. So your CH3, CH with a branch, CH with a branch, CH2, CH, CH2. Sorry, I screwed that up. Okay, so there's nothing here, and then there is one there. So you can see that this carbon is 1, 2, 3. This carbon is 1, 2, 3. So that means that the double bond goes over here. And our longest chain is 1, 2, 3, 4, 5, 6, which is hex. We'd obviously start counting from this side. This is our first carbon-carbon double bond. So hex 1, and then ene. And then we have these two branches over here, like that. So because we said that we start counting from over here because this is closest to our double-double bond. That's 1, that's carbon 2, that's carbon 3, that's carbon 4. So we have a 4 ethyl and a 5 methyl. So it's going to be 4 ethyl, 5 methyl. So we base numbering on where that double bond is, not what's going to get us the smallest number here. Okay. And this is to draw a line diagram. Okay. So 1, 2, 3, 4, 5, 6. So that's my parent, and then that double bond is on the first one, and then we have a methyl on 5, 1, 2, 3, 4, 5. So we just draw it like that, and then we have an ethyl on 4, so we just bend it once. There's a 2 attached to it. So this is what it would look like as a line diagram. Okay, so we'll do some easy board questions. Pause it, see if you can do it by yourself. This is 4 carbons. We have no branches, so 4 is bute. And then this is our first carbon double bond, so it occurs on the first one. So its name would be bute-1-ene. Okay, this one we'd have to draw out. So CH3, CH, CH, and then CH3. So you can see 1, 2, 3 sticks. 1, 2, 3 sticks. So we put our double bond into there. So we have 4 again, which is bute. And then this is bond 1, this is bond 2. So bute-2-ene would be the name of this. Okay, these two are the same, so just ignore this if they give you a structural diagram. Okay, again we have our parent is here. So it looks the same as the first one. So it's bute-1-ene. And then we have a methyl branch. So this is carbon 1, this is carbon 2. So it looks like we have a 2-methyl. Another one that we have to draw out. Just sucks doing this with a mouse. CH3, CH, C, and then we have our ethyl branch coming off. Then we have CH, so we go CH, and we have a methyl branch coming off, and then we end with CH3. Okay, so we're looking for our carbon with 3 sticks attached. This carbon is 1, 2, 3. This carbon is 1, 2, 3. So it looks like our double bond goes there. This is our parent. So 1, 2, bond 1, bond 2. So it looks like it happens at bond 2. We have 5 carbons, which is pent. The double bond is on 2, and then it's ene. I don't know why I started over here because we have 2 branches. And then 1, carbon 2, carbon 3. So we have an ethyl on 3, so 3 ethyl. And then we have a methyl on 4, so 4 methyl, pent-2-ene. Okay. So hopefully those went well, and if you have any questions, just let me know. Okay, so this was just a drawing one, so pause and see if you can do it. Draw it any way that you want. So we have 4 carbons, which is bute. We have a double bond here, and then there's a methyl over here. And I just want to make sure that I put all my hydrogens. If it's a structural diagram, you should put all your hydrogens. This carbon has 4, and this one has 3. So just, oops, extra stick here. Got to make sure all your carbons only have 4 sticks attached though, right? I drew one up here, but there's already double bonds, so 1, 2, 3, 4. So this is what it would look like. You could also draw it line diagram, so it would look like that as a line diagram. Okay, alkynes are pretty much the same thing. This is their formula. So let's say I had 2 carbons. Well, my H it's going to be 2 times 2, because that's what N is. So that's 4 minus 2. So you can figure out the formula that way. So alkynes can be identified by the fact that they have 1 triple bond. Same rule apply as alkenes. So the simplest alkene, we got to have 2. Right? So we have a triple bond here, which means we just have hydrogens coming off like that. Right? C2H2, just like we predicted. And this is 2, so it's F, and then it ends in "-ine". All of these end in "-ine". Okay, naming rules are the same. They're going to end in "-ine". Numbering begins and closes to triple bond, just like with alkenes. Right, so if we wanted to name this one, we have 1, 2, 3, 4, 5, so it's pent. I'd start counting from over here because this is closer to the double bond, right? So this is bond 1, bond 2. If I count it from over here, it'd be bond 1, 2, 3. So pent 2, ine. And then we have a branch over here. So this is carbon 1, carbon 2, carbon 3, carbon 4. So we also have a 3 methyl. Okay. Right, so this one has 2, so it's ethine. This one has 3, so it is propine. And then we have 4, which is but1-ine, but2-ine. Something you may notice here is sometimes the numbers aren't given, and that's because with propine, if I drew it like this, right? There's hydrogens on there, just pretend, right? This would still be, if I was naming this would be on the first one. So if I was naming it, this would be my first one as well. So you can't actually have it on the second one, because if you moved it to the second one, then that would become the first. So you don't actually need numbers. If you do the numbers, it's fine. But with this one, you could be on 1 or you could be on 2. If I tried to move it here over 3, well, that would just become 1 again, and we'd start counting over here. Okay, so board question, pause it, give it a go, see if you can draw it out. I will do it as well. So CH, C, CH, and then we have a CH3, CH, and we have a CH2, CH3, CH2, CH2, CH3. Okay. So we got to find where a triple bond is, and that's going to happen where there's only 2 sticks attached. So if I add sticks here, you can see 1, 2, 3, 4, 1, 2, 3, 4. That's all good. So this is our parent, 1, 2, 3, 4, 5, 6, 7. Hept. We have 1 on the first bond, 1 ine, and then we have a methyl and an ethyl that we want to do in alphabetical order. So this is carbon 1, 2, 3, 4. So I go 4 ethyl first, and then my methyl's on 3. There we go. 4 ethyl, 3 methyl, hept 1 ine. Okay, so hopefully that makes sense, and let me know if it doesn't. So one more thing that we're going to see is we're going to see these things called aromatics. So aromatics are a classification of organic compounds that have the parent benzene. So benzene always looks the same. Benzene is always 6 carbons, and it's always got these interchanging double bonds. It always has to have that, right? If I had something that looked like this, but it just had 1 double bond, well, that's not benzene. I need the 3. So benzene is a cyclic compound where there's 6 carbons and they're arranged in a ring structure. And this is called the classical version of what it looks like, where we have these interchanging double bonds. So as more science came out and as more information came out, what scientists actually found is that there's not single bond, double bond, single bond, double bond, single bond, double bond interchanging like that. It's, I'm just going to come back to that. Yeah, the double bonds are evenly distributed. So what they draw it instead is they draw it as a circle instead of that. So I can give you this in a question, and I can give you this in a question, and you'd have to know that they're both benzenes. There's 2 different ways of drawing it. So this is called the classical structure in diagram 1, and this is called hybrid or resonance structure in 2. Right? So this is the reason why this new diagram is used. And this is just a stupid picture. Like, it was from like an old textbook. It's like, to remember benzene, think of monkeys hanging onto each other and holding a banana. So these are the hydrogens, the bananas. Here's my double bond, and then here's my single bond. Double bond, single bond, double bond, and each carbon has a hydrogen attached to it. Kind of stupid, but I liked it. Okay, so common things you see benzene in: aspirin, carcinogens found in cigarette smoke. That's good enough. I know there's some extra stuff in the notes, but you don't need to know that. That was just extra information, so we're just keeping it small right now. So examples are aspirin and carcinogen, which is a cancer-causing object in cigarette smoke. Okay, that's it. I'll post an assignment, and good luck.